All right, welcome to week 8 workshop. I hope you have a good semester break. Easter is based in Bendigo. Hope you have a good time in Bendigo too. And you have some time to catch up your study as well if you miss any weeks for any subjects. Now, moving forward, we have week 8 now. As you know, we are finished more than 50% of the subjects, and we are advancing some new topics that you have not experienced before, which are very important for your structural engineering subject. Now, we have taken the lecture today morning. Yesterday, due to public holiday, we cannot took the lectures weekend, so we have a catch-up lectures today morning 9 to 11. If you can't attend and if you need to find information from that lectures, recording is uploaded on LMS. Now, for these weeks, we have 3 examples. Force methods that we have introduced to you today mornings, and I will brief you again for these workshops. Now I have a small demonstrations that I can show it to you for the force methods that I just put it here. Let me device setting and let me use the coming up. You can't see that. Can't see that. All right. Anyway, so we have this. This beam that we have. So we have a pin support, roller supports, three unknown reaction force, and was 3 equilibrium equations, and this would doable. Finding this reaction force, finding the deflections, drawing shear force diagram, and bending moment diagram. Now from these weeks, we have added extra complexity. Extra complexity meaning that if you can see this beam here, the students probably can't see this beam here. Now, for these beams, let's say you have pin supports at the left side, you have roller supports and roller supports, for examples. OK, so that's become indeterminate. Why we make the indeterminate structures? Because if I remove this book, look at that, how much deflections you will get. To reduce that deflections, you either increase the material strength or you increase the cross sections of that beam. You make 2, 3 layers, 5 layers of that beam, deflection might go away. But that is expensive also, right? So to adding materials on top of steels is expensive. Concrete, you don't want to make, if you are in the real estate or someone uncle or someone you are too young maybe, or someone you own the house, you want high roof, right? You want slim beams. You don't want something very close to your head, the beams, and you have just a roof. So everyone's looking for that kind of options that you don't want to use a lot of materials, right? So for that, one option is to put the extra support. If you put extra supports, this deflection is gone. So these extra supports create extra reaction force, and that extra reaction force add the complexity in our calculations, meaning that now here we have 2 reaction force because it's a pin supports. You have a reaction force here, third, and you have 4 reaction force, 3 equilibrium equations. We can't solve it. We can't solve it means we can't solve using our conventional methods that we learned from week 1 to week 7, right? We have done many examples on cantilever beams and simply supported beams. Now, this week, if I add extra support on the simply supported beam, how are we going to solve? How are we going to solve? Meaning, how are we going to find the reaction forces? How we draw the shear force diagram? How we draw the bending moment diagram? In that one, these force methods comes into the play. What is force methods? Force method said, all right, that's fine. How many extra force you have? He said, I have 1 extra force. Let's remove it. Let's remove it. Because engineer wants to make it simple. OK, let's remove it. Everyone say no, that is better. Deflection is there, but I'm happy. It's a determinant structure. We call these primary structures. As you know, in the lectures today morning, we call these primary structures. And primary structures are determinant structures. Engineers are happy because primary structure. So we make structures from indeterminate to determinant. We remove. Now, as you know, there was something that is pushing it up. That force is making that one 0, right? Because if you remember, there is no deflection here before. So I need to find that force to push that back. Let's say that force is 1. We don't know that how much force I need to push this one back. Let's take it 1. And let's say that deflection is something related to 1. We can find it. We have methods to find the deflections when you have 1. So someone said, no, but it's not 1. There was some value. So let's multiply that value by that real force and multiply the same with the displacement. And that will give you that unknown force. So that's the demonstrations that I'm going to show you here in this with the. Let me put this one back to my face. All right. So now, what I demonstrated just now. What I just demonstrated, I'm saying that, OK, we have learned this one. Simply supported beam and roller supports, right? And you have loading, some kind of loading. If any students can find the reaction force and shear force and bending moment diagram for that. But let's say someone add extra roller here, right? If you add extra rollers, you might have find some challenge there. So let's say you have this extra roller. Now for that extra roller, what this force method is doing, saying that, OK, that's fine. You remove that extra roller because for that it will have a deflection like this. Let's say remove this extra roller. Let's remove this extra roller. Then you will have this displacement. Do you agree with me? With some loading. Do you agree with me? So saying that, OK, then we need something. We need some kind of force, which is, let's say, this point B, that will going to give you push this one back exactly the same amount that is coming down. Right? That solve the problems, right? Because at this particular point, your displacement is 0. So let's say this is 1. And for that one, you have flexibility coefficient FBB. Let's say this is displacement. So if I multiply by some value, let's say By, then you multiply by By because we are in the elastic region and we need to find, we need to show this. If you have a, let's say, force 1, displacement 2, if the force is double, displacement is double. It's a linear relationship, right? So we can find this one. So this is just compatibility conditions. What is compatibility conditions? That compatibility conditions will be like this. And let's say this displacement delta B and this displacement delta B dash. This one, let's say down. This is down. This one plus. Both are equal to 0. And from that, we can find the unknown value. So that is the comparability, because we need additional equations to make it that equilibrium equations plus the compatibility conditions. We can solve these examples. So now let's solve these examples now. Determining the reaction and draw the shear force and bending moment diagram of uniformly distributed load. W could be any value and EI is constant. So we have given these problems and we need to draw the shear force diagram and bending moment diagram. Roller supports is here and we have this W and length L. Question is to find the reaction force, draw the shear force diagram and bending moment diagram. And this is indeterminate structures. Indeterminate structures meaning equilibrium equations are less than the number of unknown, meaning that number of unknown values. So you can see here how many unknowns. Reaction, let's say this is A, B, reaction force AY, reaction force AX, reaction force MA, and reaction force BY. 4 unknowns. 4 unknown. And 3 equilibrium equations. So we can't solve it with a conventional method. So we need to use the force methods. So there are various steps that we follow. Step number 1, find degree of indeterminacy, and that is denoted by capital D. What is capital D? Capital D is going to tell me how much quantity, how much unknown forces are extra, which are more than equilibrium equations. So for examples, for that finding the degree of indeterminacy for beam, I think 3m plus r minus 3n. That is the equations given in our lecture notes to find the degree of indeterminacy. How many members you have? You have 1 members. How many reaction force? You have 4 reaction force. How many joints? You have joint number 1, joint number 2. 3 plus 4 minus 6, 7 minus 6, degree of indeterminacy is 1. Step number 1 was very simple. You can find degree of indeterminacy, right? There are 2 equations. You don't need to remember that. There are truss equations, and for beams, that's 3m plus r minus 3n. M stands for how many members you have in the beam, how many reaction force, and how many joints. Substitute a value. And what's the meaning of degree of indeterminacy? Degree of indeterminacy is giving me the numbers that will be the extra quantity in the system. Extra quantity meaning you have 3 equilibrium equations, but you have 4 unknowns. So that difference is reflects here in the degree of indeterminacy number. So this degree of indeterminacy will help me to draw the primary structures. Draw primary structures. Now, to draw the primary structures, you have this original, this is a real beam, W and length L. So this is the real beam. Now to draw the primary structures, we have a reaction force AY, AX, MA. And you have a reaction force here RB, let's say. So I need to remove one force because that's telling me here. If you want to draw the primary structures, if you remove one force, that become your primary structure, and the primary structures would be determinant structure. So I have one options here that I can draw this cantilever W length L, and I remove this I make it redundant. Redundant means let it go, that RB. So that is become your primary structures. Everyone understand how to draw the primary structures? So exactly the same real beams. Degree of indeterminacy 1 is telling me to remove one redundant force. There is a one catch. You can't randomly remove that ones. For examples, here you have another options as well. You keep this one roller, you can make this one as a pin, and this is, let's say, MA, and still you can work through because you make this as a redundant. That is also works, right? You can make it the fixed supports into the pin, and that works as well. And I think there is a reaction force RB will stay here. That is another, there is no rules which way you're gonna make it. That's your user defined. But this one looks more user friendly because we have some equations. You can work on this one as well, but I will choose to go for these options. Right, there is a one conditions that when you make a primary structure, the primary structure should be stable. Right, stables meaning that it should not be in the space. I give you one examples here. Let's say this is a pin supports, roller supports, roller supports. What is the degree of indeterminacy here? 1 here, 1 here, 1 here. Degree of indeterminacy is equal to 1. You can see that. Now there are a couple of options. Meaning you can make this as a redundant. That is the one options. You have another options that you can make this one as a redundant. That is the second options. Now there is a third options that you can make this pin as a roller. Option 1, option 2, option 3. Now option 3 is not going to work. Of course, he has a tree one and you can make the primary structures, but it's a skateboard. It's not stable. It's you see the space, the beam is moving. You can see there is no restraint in the x directions. So when you make a primary structures, you make sure that your structure is stable. Right? So that's the conditions. That doesn't matter which one you're going to remove. There is no any rules here. The rules only saying that your structure, the primary structure should be stable. Right? So that's the information. This is just an additional information for you how to draw the primary structures. OK, degree of indeterminacy. Any questions in finding degree of indeterminacy? One simple equations. Number of unknown value minus equilibrium equations, that's number is degree of indeterminacy. Based on degree of indeterminacy, you can draw the primary structures. You remove those, you select redundant forces and remove them.
So
yes, please.
Basically, just downgrade a support by a grade as long as it stays fixed, and it's the easiest way to do it.
That's right. Okay. Easiest way to do it, that is for us.
Yes, yes.
That's not in the theory. But you are right. We need to downgrade the structures by the number that we get in the step number 1, which is degree of indeterminacy. And that's determinant structures. Yes, please. There are 6 equilibrium conditions, by the way, in the 3D. In X, some of the moments in the X, and force in the X. Some of the moment in Y, some of the force in Y. Some of the moment about Z and force about the Z. But we are working in 2D plane. So for that case, we are removing those 3. We end up with 3. Now, you need to think, what is equilibrium? Equilibrium is basically saying that their structures should be staying in that positions. That is equilibrium. So if this book is in equilibrium, what does it mean? That it has a gravitational force. All the forces coming on that beam is 0. This one is not rotating, meaning that all the moments coming on in any direction. If you take equilibrium can be make it more than 6. There is no problem. If you create another axis in between diagonal axis, and if you creating the moments about that one, it should be equilibrium on that other axis as well. But to make it simple, here we just work in a Cartesian coordinate or whatever the coordinate, the principal axis x, y, and z, and so on. So what is equilibrium? Structures should be staying in that positions because we are not working with the space structures like who are satellites and so on. Yes. Text works, yes, that's also another way to say that. Here you can say another way that you have a 4, take away 3, straight away you can do 1. Right, that is not an issue for that. But when you have complex beam like this and number of members and so on, so this equation is another option as well to verify. So basically, as I mentioned, D is number of unknown force, take away equilibrium equation, and equilibrium equation always 3 for our course. All right. Any other questions? So now, as you know, these guys, when I remove this one, this guy will have these ones. Do you agree with me? Let's give them name delta B, because before it was like this in the real structures. But I said I don't want these supports because this is causing troubles. It's a troublemakers for me in my analysis. So let's forget about the support B. So when you forget about support B, it will deflect delta B. Do you agree with me? So let's find this delta B. And there is a virtual work methods. In week number 7, we learned virtual work method to find the deflection in the beam. So we can use the virtual work methods, or we can use straight away the in our lecture notes. We have a table. Week 8 lecture notes, and there is a tables that will give you the deflection straight away. uniformly distributed load cantilever here. So here you go. We need to find the maximum deflection. So minus W L to the power 4 over 8 EI. Why I put minus? Because it's downwards. So therefore I put the minus sign. All right. So everyone okay with that? So first we find the deflections delta B. In your assignments, you may not be able to use these tables straight away. If you have a loading and the beam that is not sitting into these tables, the tables is a standard beams and supports and the loading. So if your beam is not sitting, then you need to use the virtual work methods to calculate the delta B. And if you don't know, in lectures I have demonstrated the full examples how to use the virtual work methods. All right. Any questions there? Finding the deflection in delta B in primary structures. To make a primary structures, immediately when you make a primary structure, there is a deflections, by the way, because you are disturbing the structures. You're removing the support somehow, or there is a moment or rotations, deflection or so. In that case, if I make this one, then this will have a rotations theta A. So you need to find theta A in that sense. Okay, if you choose that options. But here we choose that option, so we find the deflections. So you need to find in the primary structure shape either deflection or rotation. So everyone okay? Now once you find these deflections, then okay, let me draw it again for you for the concept wise. This is our real structures A, B, L, W. Now what we done? We draw the primary structures by removing this one, and then we calculate this delta B. Now we don't want this W because it's already there. We want something that going to push it back by the same amount. Do you agree with me? That you can see on the first these figures that delta B is coming down, but I want some force that will going to push that beam back to the original positions because we have a roller here. So that one will cause, let's say, FBB. F stands for flexibility coefficients. BB stands for at the point B, load is applied at point B, finding the deflection at point B. So FBB. When I apply 1, there is a displacement. We don't know. When you apply 1, there is a displacement FBB. But let's say this one, this is not 1, right? Actually, there is not 1. There is some force BY. Let's say 1 multiplied by BY. The force we don't know, that is multiplied by, and that force is By. So 1 multiplied by By, so the displacement also multiplied by By, because displacement is linearly proportional to the load. In that case, we have, let's put that delta dash B, because here we just put the notation delta B, we put the notation delta B dash. Everyone okay with that? So far so good. So if I superposition these two figures, superposition means putting one on top of each other, I will get the original one. Do you agree with me? That here you have this low, here you have this. I put this one on top of this one, then I will get this. Do you agree? And I can say that delta B, which is going down, minus delta B plus delta B dash equal to 0. Do you agree with me, right? That you have this deflection, and then we can find By. Once you find By, then most of the problems are solved. Right, so let's do that. One is done. Look, these force methods are quite simple. Only challenge is to find the deflections. If you know virtual work methods and find the deflections, others are just making that two deflections, and that's find the unknown value. So you understand the overall concept, right? So in that case, we found already delta B here, which is minus W L to the power 4 8 EI. Now let's find this delta BB dash or FBB. So we have this problem now. that it has a 1 here, and we have this FBB. So FBB is equal to, again we can use another figures in the our lecture notes. This one, cantilever with the point load. So in this case, we have this one, PL cubed on 3EI positive because it's going up. PL cubed on 3EI, P is 1, length is cubed 3EI, so is L cubed on 3EI. Right, and then delta dash B is equal to BY FBB is equal to BY L cubed on 3EI. Because you have seen here, delta dash B is equal to FBB times BY.
Are we supposed to be using formula, not the?
What, and sorry.
Data?
No,
Or we're doing B?
we're dealing with deflections. Theta can be done in a complex way. Any questions there? All good. So everyone agree with me with these conditions to write delta dash B, which is minus, plus delta dash B equal to 0. Does everyone agree with me this one? Negative because delta B is coming down. Delta B dash going up. Both will make it plus and minus equal to 0. We plug the values. Here WL square over 8EI. Please mind with that minus sign. We don't want to double the minus sign and make it positive. 8EI plus delta dash B BYL cubed on 3EI equal to 0. Let's common out EI. Let's common this L cubed as well. Which makes this gone. All right, so now the structures become like this now. Right? Now this become determinant structures because we have only 3 unknown forces. And we can use our conventional methods to find those 3 unknown values and draw the shear force diagram and bending moment diagrams. All right. So in that case, let's say sum of the moment at A equal to 0 anti-clockwise is positive. 3WL8 times L minus plus MA equal to 0. So MA equal to minus 3WL square over 8. Yeah, that's what I'm thinking.
We forgot the.
Yeah, this one.
Yeah.
Yep, thank you. So let me add in minus WL times L by 2 plus MA equal to 0. 3WL square over 8 minus WL square over 2 . Right. Sum of the force in the y direction upward is positive. AY going up, WL down, 3WL over 8, 0. All right, now we just have all the values. This is 5WL over 8. Three WL over 8. Length is L. Moment is WL square over 8. And this loading is W. So if I draw the shear force diagram, just going to use our graphical methods. Anti-clockwise negative and WL square over 8. And you can find these values once if you know all the parameters. Any questions? Anything that is not understand? If the tables is not useful, you can use the what we call these virtual work methods. Well,
if we happen to.
no, I encourage to use the virtual work methods because then it will become more
Showing actually.
more. I know there is networks on the table that can solve. Well, you can use for verifications. You know what I mean? The answers that you're going to get that you want to have a backup. So in that case, you can.
You're going to do a backup. You're just going to space gas it.
Well, that is it. But in the space gas, it will not show you.
Show me deflection angle.
Yeah, and it's not going to. Here you can see where you went wrong. So that's. Yeah, just use the long way. It will help you. Otherwise, as I mentioned, if you look at me 1,000 times, it will not going to help you. If you don't do it by yourself, you don't know what you're going to come across. And if you don't do, and believe me, with the students' experience, they will not do any extra work. Only assignments worked, and that week is finished. Right? Why would we do extra for nothing? So the assignment only the key for you to learn something for that particular week. And therefore, we try to put as many examples so everyone has a different questions at least. And you can ask your friends for help or something, some directions, but at least you can't just directly copy and those things. So it will be helpful for you to learn. Okay. So any questions? All right. As I mentioned, after completing these ones, you can take the questions 2 in your assignments. Okay. Finishing every week will smoothly finish your assignments. Otherwise, it will give you the extra overload and you need to do the revision again for all this work. Let me get another examples now. All right. I can show you these examples with the virtual work methods if you like, because we have some time. If I remove that support B, it would be very simple. You know what I mean? There is nothing scientific about it. It will not going to useful. So if you remove support C to draw a primary structure, it becomes quite complex. Probably we may not have that tables in that one. And I want you to help in the assignments, not just this tab using the tables. So I'm not sure how challenging it is. I don't have solutions, so I might screwed up. As you know, I'm getting old and I don't have those mathematical skills to focus. But let's see. I think you got the concept now that you have this pin here, you have this roller here, you have this roller here, and you have this 45 kilonewton per meter with 3.6 meters, 3.6 meters, right? So degree of indeterminacy, 3m plus r minus 3n, 3 times 2 members, reaction force, 2, 3, 4, 4 reaction force, 1, 2, 3 joints, 6 plus 4 minus 9, 10 minus 9, degree of indeterminacy 1. If you remove the support B, quite simple. It becomes the simply supported beam, and you can find the deflection at B and so on. There is no, and there is a table for simply supported B. The example one which I have demonstrated, you can follow exactly the same style. Solution are given. So let's choose the removing this point C and see what happens. Right, so let's say this is point A, point B, and I remove that point C. This is my primary structures. And when I draw these primary structures, you might have this kind of a deflections. Let's say this is delta C. Right, so for that case, we can use the virtual work methods to find the delta C. So in your extended tables, do we have this case? Probably they have, so that's okay. But we will show you virtual work methods. Yes, so see this kind of, if you don't have it, we need to have your skills to use virtual work method. So now forget about everything. The problem is on the screen. We need to find the, don't worry, this is a force method. It's just the virtual work method. We need to find the deflections. Yes, please. Well, I'm talking for last 5 minutes. Yes, it is easy for us to take the delta B, but that's exactly the same examples we have it in example number 1 to use the tables. And that would be very simple for you to demo. I want you to learn these virtual work methods as well. So if I remove the support C, I can demonstrate how to use virtual work methods with the force methods. And I have some time. So help me out if I cause any errors. Okay, focus here because I don't have solution and I might screwed up some plus and minus there. So I think in lectures I done some mistakes. I will finish that at the end of that one. I have that solutions. Now, so does it answer your questions? Yeah, you do data B, but in your assignment it will not be useful because in assignments you need to follow this, which I'm going to show you now. All right, so let's say you want to find a deflection at delta C. How we do it? I think we put the virtual load where we want to find the displacement and so on. So let's find these reaction forces first. So reaction force AY AX is 0, BY sum of the moment at A equal to 0, anti-clockwise is positive. This distance is 3.6 meters, 3.6 meters. So how does it work? So by times 3.6 meters. Then you have 45 minus 45 kilonewton per meters times 3.6 meters times 3.6 meter divided by 2. And then you have this minus 45 kilonewton per meters times 3.6 meters times 3.6 plus 1.8. 3.6 plus 3.6 divided by 2, 5.4 meters equal to 0. Now by 45 times 3.6 times 3.6 divided by 2, 291.6 kilonewton meters. H 70.48 kilonewtons meters equal to 0. So By equal to. Yes, I'm coming back. Divide by 3.6, 324. Okay, 5.4. All right. You know this part. So if I have this force here, which is 45 times 3.6, and then you have 162, this distance from here to here is 5.4 meters. Does it answer your questions? Okay, so this is 162 and that is 5.2. Everyone got this? Don't copy this one, 324. If you get different answer, tell me, because it's, yes, double check. Yeah, double check. Yes, that's what I mean. Yeah, we have answers delta B, so somehow we're going to get it. Yes, you're smiling, but you have some questions. We are going long way, and that is helpful for your assignments. All right, so some of AY going up, BY going up, minus 45 kilonewton per meter times by 7.2, AY 324 kilonewtons. kilonewtons. Sorry, what happens here? 324, 45 times 7.2. Oh, sorry. 337.5 kilonewtons. $13.5 kilonewtons. No?
45 times 7.2. Isn't that just 324?
So 324. So EY is 0, is it right? Yeah, so that's good then. So EY is 0. Okay. Everyone got AY 0? All right. No? Yeah, no, that's I'm expecting negative because you know the cantilever. Yeah, so it's not weird if we get negative. In some of the examples so far, as you know, the balcony. This is the balcony here. And this, so this one, sometimes this will get negative, this one positive, so 0. Yeah, so be expecting some negative, but 0, yeah, yeah, that's what I told you. Some weird answer might come here. So probably you need to change the space gas quickly if you want, so we can see the answers. All right, anyway, now we done this. Now we need to, I think the equations for delta C would be 0 to 3.6, M1, capital M1. And I also need to answer this one for you, how we get the radian. Do you remember that last week? And I solved that one as well. At the end, I will show you that one. And then you have again 0 to 3.6, small m2, capital M2, EI, dx2. This is what will work, right? This is the equation for what will work? I don't remember. I think that's the one. All right, so what's 3.6 and this one? So if I redraw this one, this is 0, this is 0, this one here. BY is 324. and that is 45 kilonewton per meters, and deflection at C, that we need to find. Okay. So then we will make a cut. This is the first cut. That is your this X1. And by the way, this is 3.6 meters, 3.6 meters. And we make a second cut, which is X2. Right? And we find small m1, capital M1, small m2, capital M2. Let's find capital M1 first, because that's the real structures. So this is point C, this is point C. Cut number 1. Let's say this is X1. And this is a revision for virtual work methods, by the way. Okay, so that's also one additional one. Capital M1, 45 kilonewton per meters. So sum of the moment at cut equal to 0 anti-clockwise is positive, minus M1 minus 45 kilonewton per meter times by X1 times by X1 divided by 2 equal to 0. So M1 is equal to minus 45 X1 square. M1 equal to everyone got this? Yes, everything okay? All right, so, and then we do the second cut. Point C, B has 324 kilonewtons. 45 kilonewton per meters, 3.6 meters. Cut number 2, capital M2, X2. Sum of the moment at cut equal to 0, anti-clockwise is positive. So let's do this. 45 kilonewton per meters times by 3.6 meters times by 1.8 plus X2. And then this would be minus. And this one minus 45 kilonewton per meter times X2 times X2 divided by 2 minus M2 equal to 0. No? Yeah.
Why did you click by 1.8?
So let's say this one, 45 times 3.6. 45 times 3.6. That will go 1.8 here. So from this point to here, 1.8 plus X2.
Yep.
Then minus 45 of this one times by X2 times by X2 divided by 2 minus M2 equal to 0.
Yep.
Does it work like this? Yes. Sorry, which one?
324.
Oh yeah, 324 we need to add this side. So it's quite complex, as you know. All right, let's get the 3.24 somehow. Get in here, squeeze in here, minus M2, and that's plus 324 X2 equal to 0. Right, so 45 times, sorry, 45. Just do the calculations by yourself. Don't blame me if we don't get the answers. 162 kilonewtons, 1.8 x2 minus 22.5 x2 square minus m2 plus 324 x2 equal to 0. So 45, that is minus 162, 1.8 x2, 22.5 x2 square minus m2. So far so good. Times 1.8. 291.6 minus 106 x2, 25 x2 square minus m2 plus 324 x2 equal to 0. So 324, 162 positive. Does it make sense? No? Which one?
Can you just write back, I think you've already explained it once, but the 1.8, in the brackets, 1.8 plus x2, y.
All right, let's go. 45.
Yep.
Times by 3.6.
Yep.
That will make it here.
Which is 1.8.
Which is 1.8.
Yep.
Plus x2.
Oh, because you're measuring it. Yep. Golden. Sweet. Thank you.
And then that's it.
Yep.
Right? Okay. Okay, so now M1 and M2 is done. Now we need to do the virtual work methods. We need to apply the load 1 in the directions the deflection need to be found. You remember that sentence from the virtual work methods, right? So we remove all the real loading. We will put 1 at point C going down. Okay, so the real structure's done. You happy with me with this kind of a case? Like this, we have 1 point C, point A, point B, 3.6 meter, 3.6 meters. Rules is same, that we going to make a cut exactly the same format as we done in the real. Yes, and then we will measure exactly the same directions that we going to do it with the real one. Yes. Yes, that's the negative answers. If you can't imagine which way is going, but I can see here that is going down. Why would I make my life challenging if I know? But still, if you get negative answers, meaning that your assumed direction is wrong, the displacements. All right, everyone happy? Cut. We make a cut at the same location where how we make it in the real structures. We measure x1 same points as we done in the real. We don't change it this one. Okay, don't be smart to have it different real and different one. That will screw up your integrations. All right, so let's do the calculations for these reaction forces again. AY, AX, and BY. I'm not sure whether we're going to get the right answer or not, but you will get the idea what we're going to do it. Okay, because I think there are a lot of things there. Okay, let's do the sum of the moment at A equal to 0, anti-clockwise is positive. So BY times 3.6 meters minus 1 times 7.2 meters equal to 0. So BY equal to 7.2 over 3.6. Boom. Okay. And AY going up, BY going up, -1 down, AY 2 -1. So AY equal to -1. Right? So we find the reaction forces AY -1, BY 2, 1, A, B, C, cut 1, X1, cut 2, X2. And we're going to find small m1, small m2. So let's do that. 1, 1, small m1, x1, one, x1, okay, that should be useful for us later. And similarly, we can do the another one. Point C, B is 2. Cut number 2, small m2, x2, 3.6, and 1. Moment at cut equal to 0, anti-clockwise is positive. -1, 3.6 plus x2 plus 2 times x2 minus m2 equal to 0, m2 equal to -1 plus x2 plus 2x2. m2 equal to minus 3.6 x2 plus 2x2. So plus x2. Is it right or something else? Okay, no, that's all good. I think that will get plus minus 10 and minus plus 3.6 x2 2x2. Now I can stop.
Back up to when M1 and
Capital M or capital? Yes, capital M1 here. And capital M2.
Would we have made the cut? So made that M2 have paid like calculated it come at the size of
Up to you. Well, if you at the end we will see.
Oh, so it doesn't matter.
Yes, for these equations you will get different answers. That's right. But at the end we will get the same difference in delta C. If you come left from the right or right from left, there is no rules. Okay. All right. So everyone getting the same thing? 3.6. I'm not sure. It's lot of calculation, so we might end up something wrong. But let's see. So in that delta C equal to 0 to 3.6 m1 EI dx1 plus 0 to 3.6 capital M2 EI dx2. Do you agree with me? Right, that's the virtual work method equation, and we have small m1, capital M1, small m1, capital M1, small m2, capital M2. We plug the values and we do integrations. Right. 0 to 3.6. Let's take the EI out. We forget about EI first, so we no need to write them. 0 to 3.6. Small m1 minus x1. Capital M1 minus 22.5 x1 square. EI we not need to worry about, so dx1 plus 0 to 3.6. Sorry?
I didn't realize you could be brackets and stuff.
Oh yes, that's a big bracket. So minus 3.6 x2. And then you have these big equations, minus 22.5 x2 square. X2 square plus 162 x2. And then minus 291.6 dx2. Right? So um, 22.5 x1 square over 2. And that is 0 to 3.6. Right? Positive x1 square cubed 3. That's right. Positive 21, not cubed. 4 and 4, right? Right. Still a lot of small things. Probably I'm not sure. All right. And there is a big expansion here, which would be challenging again. Okay, so let me do this expansion separately. Right. All right, so let me know if you get the same answers when we do the integrations. 5 x to the power 4 on 4 plus 243 x2 cubed on 3 plus 874.8 x2 square on 2 1049.76 x2 6. You have a scientific calculator, probably you can plug in quickly. No? Tell me if it is something is does not match. Yeah, you got the same? Very good. You got different? Well, this kind of long calculations you need to do it in your assignments. And you need to attention on that one.
I marked up sign.
Yeah, so that's right. So therefore you okay now all? All right, so now we just plug the values and then do the calculations, and I think most of the big part is done. All right, so here 22.5 times 3.6 to the power 4 divided by 4, you get 944,784 plus 5 times 2 check if you get same, and that is your delta C. We are not putting EI, that is the EI value, but it will get 0 when we have a multiplications. I will put that sounds because there is a faulty computers. Just check the calculations. I'm coming back in 1 minute.
Get that. Yes. No, he didn't get that one. He got 1.895. That's pretty well, this one.
Something wrong or everyone okay with that one? Delta C. You got different answer from where? Here or from everywhere?
I got the same as the line above.
As you get line above, and then you do the calculations, plug in. And then
And I got 3,700 and point.
what about this one? First one, okay?
Yes. Yeah.
And this one wrong. This one is same for you, right? Oh, but we need to put the minus here. Then it becomes 0.
No.
Did that differently for your different answer?
Different.
You got different answer for this one,
Yeah.
and that would be positive minus 22.5 times 3.6 to the power 4 divided by 4. Let's put this in that way. I'm getting the same one. Which one I get wrong?
I don't think you guys did the first thing there.
Huh?
We get the same as you.
Oh, yeah. I think you're right.
All good?
Yeah.
So this one minus this, and I plus, then it came plus 944,784. Surprisingly both same. And delta C equal to this one. One big job is done. Right? Now, as you know the story, probably you forget the story because we are come all long way. As you know, we remove this one, so we need to put it this back. What is put it back? That. Do you agree with me? That we need to do all this calculation again, but I think our virtual work methods and this one matching. If you remember that we have a one is going this way, so probably we can utilize that. Probably in your assignments, if you come across, we expect that you can do the same. You got my point, right? Because what happens here, we need to push this delta C back to 0. That is 1, we don't know, and that is 1. So I think we can find that deflections FB. I think the deflection would be like this and like this. That let's give them name FCC, right? Fluxor coefficient FCC, and that is due to 1. And then you multiply by CY and multiply by CY. That is give you delta deflection C dash. So let's say delta deflection C dash is equal to, oops, C dash is equal to multiply by CY. So CY FCC. Right? Any questions? So we can find this delta. We found delta C. Now we can find delta C C dash. But I think forget about CC. Just one with FCC. And if you have one FCC, we can utilize these our virtual work methods. So FCC equal to, I think FCC equal to 0 to 3.6 small m1 capital M1 over EI dx1 plus 0 to 3.6 small m1 capital M1 EI dx2. Right? Our structure is, by the way, this one. C A B 1, and we need to, oh sorry, this is supposed to be going this way. FCC, right? So that is a real structures. For real structures, capital M1 is, I think this X1, this one, right? Because we done this one, I think it's opposite. So if it is going this one, so that would be positive X1 because our this one going this way right now. Right, so if it's going this way anti-clockwise, so positive X1, and that would be positive and negative. So capital M1 equal to positive X1, capital M2 would be 3.6 minus X1. Does it work or no? Or would be different? That is the virtual results, but in the virtual one, the load 1 is coming downwards. In this one, upwards. And then you have small m1, same thing. Small m1 minus x1, small m2 minus 3.6 plus x2. This is x2. Right, so positive 3.6. So I think it's gonna work here minus 2. Do you understand that or kind of? Yes, sorry, no, not really. We have how do I explain? So we have these structures now, right? And our job is to find a deflection FCC dash, right? So the real structure is this one, and the virtual structures is this one as well. I think we just need to have it same. So this one would be x1 and 3.6 x2. So this is a real, this is a virtual. Virtual loads going in the same direction where you want to find a displacement. Right? So you have real structures. This is virtual structures. For the real structures, M1 is x1. If you make a cut here, then you will get x1. If you make another cut here, you get 3.6 minus x2. For this virtual, you make a cut here, you get x1, small m1. If you make a cut here, 3.6 minus x2. Right? Or it will not gonna work. I'm not sure. Let's say FCC is equal to 0 to 3.6 x1 x1 square over EI dx1 0 to 3.6 then 3.6 minus x2 3.6 minus x2 dx2 EI. So 1 over EI x1 cubed on 3 0 to 3.6. Now this will be 3.6 square 12.96 7.2 x2 plus x2 square dx2 oh that's better. We can do the space case and check it if it's CY is correct. Plus and minus integration, something wrong, but that's the overall strategy. You got the idea? Once you get the CY, we can solve it. Others. Yes, please.
I thought it was those added together.
Okay. Therefore, I go through all the procedures with you. Okay, let's say there are two ways you can do it. First way I'll show you. Deflection downward minus. Deflection upward positive. Or deflection at C equal to deflection at this one. Both way gonna work. So the minus coming because this deflection is downward. So therefore I put minus there. Otherwise you can do the same thing. You can bring this one across. Delta C dash minus delta C equal to 0. Does it answer your questions? So downward displacement minus, upward displacement positive. So therefore we have minus. Or you can say delta C equal to delta C dash, because this displacement, by the way, that we found equal to this displacement. That is both equal. You can substitute a value, both equal, you can find the unknown value C1. Right? Or you can do the compatibility equation saying particularly this point, downward displacement is negative, upward displacement is positive, equal to 0. All right, I'm not showing another methods now because I'm running out of the time. Meaning that another methods, meaning that yes. Okay. Does they have it? Oh yes. So in that one, that's okay. So support B settled downward 75. So that's good. Thank you for that. So we can include that. So delta C dash minus. Oh sorry. Yes, minus delta C plus delta C dash minus 75 millimeters equal to 0. Right. So still fine. I think the EI will not going to work in this case. So we need to plug that EI value minus 1889.568 over EI plus delta C dash would be CY 31.104 EI minus 75 equal to 0. Now, thank you for pointing it out. What is happening here? Instead of, otherwise you can do this equal to 75, right? Because this is not 0. You got my point? Because this support is settled. Support B or support C?
B.
Yeah, so in that case, I think we can't use this method. I think support B is settled by 75 millimeters. No, then if we find this 475, let's say in that case, if you find that one as a redundant force, therefore I think from the start we should choose this redundant force. In that case, minus delta B plus delta B minus 75 equal to 0. Settle downwards meaning minus. Okay, so you follow exactly the same procedures. Minus delta B plus delta B dash minus 75 equal to 0, and you can plug those values. Yes. But I'm not sure whether this what's the deflection at Do we have answer for that one? What is the reaction at? No, reaction at C. They don't have it. Yes, no. Yes, please.
Space gas says 60.75.
It's good.
But how do you model that in space gas with the B deflection?
I'm not sure. I need to check the settlements. Probably there is a way to.
Yeah, if I just put that node lower, it just thinks that those beams are angled. It doesn't think it's deflected.
Yeah, I need to check if it is not going down, how this analysis going to work. So I think the method that I have presented is right. We got the same answers as you check, right? 60.70. That's what we got, right?
Yeah, B doesn't deflect.
We got 60.75, right? Yeah, but point C is not affecting by the B settlement. But when we have a B as a conditions, we can find those settlements. Can I show you that B settling down in that way?
Trust me.
All okay now? Settlements is nothing, but when you have a instead of 0, you put that settlements, right? Because as I excel, there is a displacement is 0. The displacement is not 0. Displacement is 75, or you can just at that particular point, what would be that one? So let's do the truss one. All right. Area is given, Young modulus is given, so everything is given. So it's a very complex problem. So I'm sure how far we can go. That's, let's say, determining the axial force in member BC. Where is it? Member BC? Oh, here. We need to find the force in these members, right? Let's find if it is determinant or indeterminate. Degree of indeterminacy equal to m plus r minus 2n or something. M plus r minus 2n. Yep. Number of members. How many members you got? 1, 2, 3, 4, 5, 6 members. How many reaction force? 1 pin, 1 roller. So 1, 2, and 3. 3 reaction force. How many joints? 1, 2, 3, and 4 joints. 9 minus 8 equal to 1. Degree of indeterminacy equal to 1. Right. So when you have a degree of indeterminacy 1, we make these members make a redundant. We said these members will go. Right? Like in the beam, we remove reaction force. Here we remove one member force. So in that case, we have structures like we have structures like this. We have a pin. We have a roller. A, B, C, and D. And we have a 40 kilonewtons here. We have a 30 kilonewtons here. All right, now, and we have an area, different area is given for these members. Now we make this, when these members will goes, then we will have a deflections here. There is some displacements here. Let's say delta CB. Do you agree with me? When I remove these members, this point C will deflect downwards. Do you agree with me? Because this members was trying to put that in that positions, right? So when I remove that members, it will have a deflection delta CB. And let's find this deflection delta CB using the virtual work methods. Right? So in that case, what we need to do it, I think we draw these all the all right. So first of all, we're going to find the reaction forces. Sorry, one here. One here. Now let's find the reaction forces. Sum of the moment at D equal to 0, anti-clockwise is positive. So let's say this is AX. Minus 40 kilonewtons. Times by this distance is 1.2 meters. Minus 30 kilonewtons times by distance is 0.9. And yep, AX times 0.9. So if I solve that, 40 times 1.2, let's say dx and dy. Right? We find the reaction forces. Now we're going to use the joint methods to solve these problems. Let me see which one we're going to use. 1, 2, 3. 1 and 2 here. 1 and 2 here. Yep. Joint B can be used. We can solve this. Cancel this. Okay, let's do the joint number B. FBA, FBD, 0.9, 1.2. 1.5. And we have 30 kilonewtons going this way. So sum of the force in the y direction upward is positive. FBD equal to 0. Sum of the force in the x directions, FBA negative. So FBA equal to minus 30 kilonewtons compressions. Right? We do joint C. $40 kilonewtons. FCA, FCD, 1.2, 0.9, 1.5. Sum of the force in the y direction upward is positive. Minus 40 minus FCA times 0.9 on 1.5 equal to 0. FCA 40 times 1.5 over 0. You got minus 66.67 kilonewton compression. FCD minus FCA times by 1.2 over 1.5 equal to 0. FCD minus 40 times 1.5 on 0.9, 0.2 on 1.5 equal to 0. Forty times 1.2 over 0.9, you get positive 53.33 kilonewton tension. Joint A. Sorry, 83.33. Sorry, what is happening?
So joint A was 30 in.
Yes, 30 from that's right. From here, 30 in. From here, 30. And FAD and FAC. 0.9, 1.2, 1.5. Minus 30 plus 83.33 plus FAC times by 1.2 over 1.5. right? And FAD going up plus FAC going up times by 0.9 on 1.50. Anything else? We found this, I found this. We found everything, right? Let's put that one here. Copy. All right, so what we found so far, FAC is 40 positive, right? We found, sorry, what happened here? FAD, sorry, this is FAD. FAD, let's number them. 1, 2, 3, 4, and 5. So N1, N2, N3. This surface flow is frozen. N3, N4, and 5. And we put those values. So NAD is 3, so 40 kilonewton positive. And 1 AB. AB is minus 30, BD is 0. All right, let me just explain you this way, because I think this surface flow is stop working. Yeah, too many page and it's overheated because it's 2 hours. It can't handle too much calculation. All right, so let's try this way. Just give some airs to. One is AB done. AB is how much? Minus 30. BD is 0. So BD is 0. So 4 is 0. Sorry, what is happening here? AD. 3 should be 40. Yep. 3 should be 40. This would be minus. And BD is 0. 5 is AC. AC minus 66.7. And 53.33. Positive or negative? And positive. Okay, kilonewton I did not write. Now, everyone okay now, this one? what we do it next? Now we're going to put the virtual load and we find a small n. Where we're going to put the virtual loads? We're going to put the virtual. We're going to find all the real loading in these systems and we're going to put the virtual load. Let me put that. We remove everything. We remove this and we put the virtual load here 1. Right? In the directions where we want to find the displacements. We want to find the displacement downward this one. And from that, we're going to find small n1, small n2, small n3, small n4 and small n5. That is given here. Sorry. Which one? The arrow? That is in the next one. Okay, the redundant force. And we find N1, N2, N3, and N4 reaction force and joint methods. Right, and that's way we can find the deflection delta CB. Right, from C to B. Right, and deflection delta CB would be capital N1, E1, A1, A1, and that is 5 times. Possible, right? You substitute that value. And then what you said that you need to have a second one. That is for our force methods. Do you remember that when we removed that force, we need to put it back, that 1. So you have 1, put it back. Let's remove that. And that is your structures now. You remember that, right? From the beam that you remove all the structures and we want one force that will cause that displacement to be 0. So in that one, let's put the flexibility coefficient FCB. And we calculate FCB for that one. And for this case, virtual and reals are same. In that case, we have small n square. Or you can have a small n1, L square, E1, A1, and so on. Right? And then you make it both equal. That delta CB plus FCB. And then force FCB equal to 0. You found this, you can able to find this unknown axial forces. Right, you understand the overall methods because there are 2 joint methods. There are 2 examples, by the way, joint methods. The one joint methods, real one, and then you put the virtual ones, and then so on. So you find 2 deflections, make it equals, and that's you find the unknown axial forces. Right? Any overall questions? I know it's a lot of information, but I just want you to give in 2 hours as much information as possible. Okay. Otherwise, in that examples questions, so in 5 minutes we can finish it because there is a tables that we can use it straight out. But I have for your assignments there is a beam examples, I believe. So there's no truss examples. There is a beam example. So we have done extensive practice on that one. And I think there is no settlements in the assignments. There is no, I don't remember if there is any settlements. In some questions, maybe settlements. But with settlements also possible to do it. Any questions?